Hi Level 3s, welcome back to 3.6 Aqueous Chemistry. This is Lesson 9. This is the last lesson on KS. So the learning objectives for today are to recap solubility problems. And so what we're actually going to do is do exam questions 2015 to 2017. And I'll leave 2018 and 19 for you to do for homework. We're also going to recap equilibrium graphs, but I'm not going to do that in this video because it's not essential for your understanding. It's a little bit of bonus for the kids who are doing kind of scholarship. Okay, so here's the 2015 exam. It says sufficient calcium carbonate is dissolved in water to make a saturated solution. Straight away, because it says saturated solution, we know that we are in equilibrium. It says write the equation for the equilibrium occurring. So that's nice and easy. So when you write the equation, it's starting with the solid and forming aqueous ions. Remember, you never need to include water in this equation. And that's purely because aqueous means dissolved in water, so it's done for you. The next part is to write a KS expression. So KS equals products divided by reactants, so Ca2 plus, CO3 2 minus, and we don't divide by the reactants calcium carbonate because it's a solid, and solids and liquids are never included in a KS expression because their concentrations don't actually change. Now it says calculate the solubility product. Solubility product is the KS. And it says if the solubility is 5.74 times 10 to the negative 5. So I'm going to skip to the next slide to help with the calculation here because I've already entered it all for you. Okay, so here's the first two that we already did. Okay, to calculate the KS, we know that we have to do x times x, which is the same as x squared. X is solubility, and they'd given you the solubility in the question is 5.74 times 10 to the negative 5. So you just had to square it, and the answer is 3.29 times 10 to the negative 9. So please note all answers to 3 sig figs, okay, and there's no unit for a KS. Okay, so back to the question. Some marine animals use calcium carbonate for their shells. Increased acidification of the oceans poses a problem for the survival of these marine animals. Explain why the solubility of calcium carbonate is higher in an acidic solution. Use an equation to support you. So what's happening here is if we're adding H3O+, okay, it's going to react with the carbonate ions, which are basic. So that's going to reduce the concentration of CO3 2-, so the equilibrium is going to shift to increase the concentration of CO3 2-. It'll do this by shifting to the right to replace the lost CO2, and therefore more of the calcium carbonate will dissolve. And this is the equation that you must be able to produce in your exam. They love asking this one because it's a little bit harder than just H3O plus OH- goes to 2H2O. Okay, so 2H3O plus CO3 2- forms 3H2O plus CO2. So I hope that makes sense. So therefore the solubility increases for this one. So the next one, team, is here. Show by calculation that a precipitate of lead hydroxide will form when 25 mils of sodium hydroxide at a pH of 12.6 is added to 25 mils of 0.0421 moles per litre. And that must be of lead nitrate. Oh, it's just popped down here, of lead nitrate. So let's first of all work out, like, you don't have to do this first part, but it's quite good just to make sure that you're all good. So NaOH plus PbNO3 are what they're adding together. And when you add two aqueous solutions, a precipitate forms, and you work out what's happening, the N switch, so then sodium nitrate forms and lead hydroxide, and they've told you lead hydroxide is the precipitate, so I'm just doing it to show you what's happening. Okay, so remember when in IP1 you've got to work out first of all what are the concentrations of the ions that we're looking at, and then we have to dilute them because when you add two solutions together they become diluted. So the question says 25 mils of sodium hydroxide with a pH of 12.6. If they give you a pH, you can actually convert that pH to an H3O plus by going 10 to the negative pH. So 10 to the negative 12.6 will give an H3O plus, but we actually need to know the OH minus of the compound. So therefore, once we've got the H3O plus, we can work out OH minus by doing Kw divided by the H3O plus. So that would be the first step that we do there, and I'll show it to you on the next slide. And then the other thing is that we look at the concentration of the lead nitrate. Lead is the 1 factor and the nitrate's the 2x. So therefore that's just the concentration of the lead ions that we'll use. So Pb2 plus is going to be 0.00421 moles per litre. And once we've worked out this OH minus, we then need to dilute both of these and then we plug them into our IP. So I'll go through this here. Okay, so there's the concentration of H3O plus. So we need to work out OH minus by doing Kw divided by H3O plus, and we get 3.98 times 10 to the negative 2 moles per litre. So we're interested in the OH minus here and in the lead. So you can see here that sodium hydroxide are 1 to 1, so they've got the same concentration, but lead nitrate, there's twice the amount of nitrate as there are lead, but we're not worried about nitrate or sodium because they're just spectator ions. So the next step is to dilute those. Okay, so we dilute by taking the original concentration, original volume divided by new volume. Now here you can actually see that we've doubled the volume, and when that happens you can just half the concentration. So these concentrations are halved, but I've just done the full calculation to show you. So next what we just need to do is plug into our IP. So if that's our KS expression, IP is exactly the same. We call it IP though because it's not at equilibrium. So that's why we have to change what we call it. So IP, so then we just plug in these values. So Pb2 plus here, goes here. And then we need 2 times, oh sorry, there's the hydroxide, so we just put this hydroxide here, and you don't do the 2 times, just because that is actually the concentration of hydroxide you've got, so you don't have to account for the fact that there's going to be more of it. That's actually the concentration, but you do need to square it. And when you plug those together, you get your IP, and so we can just compare that back to the KS. So the KS in the question, we actually calculated, and the KS was 3 point, oh no, that was calcium, sorry, let's find the IP question here. Sorry, the IP is 8.0 times 10 to the negative 17. Okay, so that was 8.0 times 10 to the negative 17. So our IP is way greater than that KS, and that means that a precipitate will form. So I hope that makes sense. Let's now move on to 2016. So silver carbonate is sparingly soluble. They've given a KS and a molar mass. It says write the solubility product. So some of you will be able to jump straight into it, but I highly recommend doing an equation every time to make sure you don't miss that there are 2 silver ions for every 1 carbonate. So the KS is going to be Ag plus squared CO3 2 minus. So that's your KS. Now it says calculate the mass of silver carbonate that will dissolve in 50 mils of water to make a saturated solution. So for this one here, they've given you a KS. So what you actually have to do if they've given you a KS is solve for solubility, which is X. And once you've got a concentration, we know that we can relate a concentration to a mass using the molar mass. So this is how we do it. So here we're making solubility S, but it could be X, it doesn't matter. So if you've got Ag plus, it's going to be 2S or 2X. Carbonate would be X or S, and so that's going to be 4X cubed. So we know that if we do the cubed root of your KS divided by 4, you will get this answer. And that's your concentration, that's your X, that's your solubility. So once we've got the solubility, we can turn that into a number of moles by timesing by the volume. They said 50 mils. And so therefore we get this many moles, and if we've got the moles, then we can work out the mass by doing number of moles times the molar mass, and you get 1.75 times 10 to the negative 3 grams. The molar mass was given in the question, I believe it was 276. So you just had to times this number of moles by 276. So I hope that makes sense. So let's go back to the question now. It says explain how the solubility will change if added to 50 mils of 1 mole of ammonia. Support your answer with balanced equations. So this one here, whenever you see ammonia, alarm bells really should be going that what you're actually going to form is a complex ion. And so these Ag plus ions are going to add to 2 NH3, because this is the one where there are 2, to form AgNH3 2. Okay, plus. Okay, now if that happens, it's going to remove these Ag plus ions from our equilibrium. So the concentration of Ag plus is going to go down. And if the concentration of Ag plus goes down, the equilibrium is going to shift to increase the concentration of Ag plus. The equilibrium would move to the right in order to replace it. And that means you're going to get more of Ag2CO3 dissolving, which means that the solubility will go up. and that is all written here. Okay, so more dissolved, solubility goes up. So if we look at part D now, part D says show by calculation whether a precipitate of silver carbonate will form when 20 mils of silver nitrate is added to 35 mils of sodium carbonate. So in this one here, they're doing silver nitrate added to sodium carbonate. Now you don't have to do these equations. I just do them because I think it helps students make sense of what they're doing. But they do tell you what the precipitate is anyway, so it kind of is done for you. But anyway, so that's the balanced equation. This is the precipitate that we're working out from. So the first thing we do is work out the concentration of the ions we're interested in. So we're interested in Ag+. Okay, but the Ag+ comes from the silver nitrate, and this is a 1-to-1 ratio. So we first just grab whatever concentration of silver nitrate there was, which was 0.105. We now look at the concentration of carbonate, which this is the 2 and this is the 1, so the carbonate's in the 1 ratio, which means the carbonate concentration is going to be 0.221. Now remember, when you mix two solutions together in chemistry, they dilute, so we have to do dilution. So the silver nitrate was 20 mils, so 20 is the original and the new volume is 55. Okay, and this one here, the carbonate, was 35 mils, so therefore that one's going to be 35 over 55. And I'm going to switch slides so you guys can see those diluted concentrations, but the next step would be just to plug them into the IP, which is the same as the Ks expression, so it would be Ag plus squared times CO32 minus, and so you just plug in those two values and then we compare it to the Ks to see which one's bigger. So here we go, here's the dilutions. Okay, we plug them into the Ks. Key thing is that you don't, just remember, you don't need to times the silver by 2, because this is actually the concentration of silver that we've got, so we don't need to make to do that one. And the IP is 2.06 times 10 to the negative 4, which is way bigger than that Ks, and so therefore we will see a precipitate. So final exam for today is the 2017. It says write the equation for the equilibrium of copper hydroxide. So CuOH2 solid goes to Cu2 plus 2OH minus, and all should have states, so they're both aqueous. Write the Ks, so Ks equals Cu2 plus and OH minus squared. And now it says calculate the solubility in water. So solubility is when you solve for X. So Ks equals X times 2x squared, which equals 4x cubed. So X is going to equal the cubed root of your Ks divided by 4. And so you just need to plug that in. And so here's the answer here. 2.29 times 10 to the negative 7, 3 sig figs, and has to have units moles per litre because it's a solubility. Final part of the question, explain why the solubility increases when HCl is added. Well, if you've got this equilibrium up here and you add some H3O plus ions, they're going to react with those OH minus to produce H2O. And if that happens, the concentration of OH minus in our equilibrium is going to decrease. So our equilibrium will shift to increase the concentration of hydroxide ions. It'll do this by shifting to the right. And if it shifts to the right to replace those lost OH minus, you're going to get more of the CuOH2 dissolving, and that means that solubility is going to increase. So I hope that's made sense, and that's actually the final exam question that we were going to go through today. And yeah, so I'm hoping this is fully making sense to you all now. If you can do these questions, you're doing superbly. That's as hard as they get. Please now do 2018 and 19 on your own, and I will see you next lesson as we move on to the next topic. Okay, thanks team. Bye.